So it turns out that the units of your variables, both the predictors and the response variable, can matter a great deal for at least a couple of reasons. Number one, they can really contribute to or detract from the interpretability of the model. And number two, they can also be important for computational stability. For example, don't be fooled into thinking that a model coefficient like a slope, for example, is practically significant because it's really big, like some number like 93 million, or that it's practically insignificant because it seems small in magnitude. The units really matter. For example, 93 million miles, that's a long way, but that's equal to one astronomical unit, or 0.0000158 light years. Okay, this it appears to be a small number, this appears to be a big number, but when you attach the proper units, they're exactly the same thing. They're exactly the same thing. So it's important to use units that make sense for your problem at hand. On the other hand, it can also be important to use units that will scale your variables so that they're more or less, on the same scale. If your model matrix X has variable observation values that are, say, really, sort of not so out of the ordinary for one variable, but very large for another, or very small for another, it can be difficult or actually impossible to invert X transpose X. There are a lot of different ways to get around this problem. There are a lot of different ways to rescale data. Sometimes people will rescale the data so that the minimum value is mapped to -1 and the maximum value is mapped to 1, and then all the other values fall in between there. Or sometimes they map the minimum to 0 and the maximum to 1. One of the most common methods, though, is to do like we've already seen, to standardize variables in the common way where you take the variable observation value and subtract, say, the sample mean, and then divide by the sample standard deviation. Or if you're dealing with a population, you subtract the population mean and divide by the standard deviation of the population. If you rescale a predictor variable, xi, like that's the ith, or think of this as the ith predictor variable, if you standardize all those values by subtracting, say, the sample mean of the values on the ith predictor, and then you subtract the mean from each one of those, and then divide by the standard deviation, the sample standard deviation, it's not going to change the results of the t or the f tests for significance on those coefficients. It also isn't going to affect the response variance estimate, the common sigma squared. It's also not going to affect r squared, but it will change the slope estimate. It makes sense, right? Slope is rise over run. So for example, if I want to talk about something as simple as a rate of change, distance over time, I could talk about something moving at a rate of 10 miles per hour. Or if I note that my predictor variable there is, say, time, and 1 hour equals 60 minutes, then another way to say that is that the object is moving at a rate of 10 miles per 60 minutes, or 1 mile every 6 minutes. Okay, so the slope effectively changes, at least the numerical value of the slope. But we've actually changed the units, so we haven't actually really changed anything. It's just sort of changing the way we look at it. The computers don't know anything about the units that are attached to these things. It's only the computers are only going to deal with the numerical values, and so we have to be sensitive to that and understand that. If we rescale xi, the ith predictor, to say something like this form. That is, if we add some value to it and then divide by some constant. See, this is actually the same form as, or the way we usually standardize. Take C1 to be, say, negative the sample mean, okay, and C2 to be the sample standard deviation, okay, then that's exactly standardizing, in the usual way. But if we think of it this way, then what happens to our partial slope estimate there, beta I hat? It becomes C2 times beta I hat. And rescaling the response variable by adding some constant and then dividing by a constant has no effect on the t and f test, but we'll rescale the response variance estimate and the model coefficients by the denominator here, C2. That is, the common estimate for the response standard deviation then becomes what it was before, divided by C2, and the model coefficients then get divided by C2. Let's demonstrate with an example from the Faraway text. I'm going to pull these things up into RStudio here. I've got the first thing I'm going to do is I'm going to load this Faraway library, and then I'm also going to take a look at this data set called savings. Let's run those first two lines there. And see, when you do that, it looks like here's the information on the savings data appears, at least in my RStudio, over in here. Okay, savings data frame has 50 rows and 5 columns. The data is averaged over the period 1960 to 1970, okay? So the first variable in this data set is the SR variable. It's the savings rate. It's the personal savings divided by disposable income. Second variable is POP15. That's the percentage of the population under the age of 15 years. So if you can sort of think of it as, if this POP15 number is large for a particular country, then that country is sort of young in a sense. Then we have POP75. That's the percentage of the population over age 75. The larger that number is, then the sort of the older the population is in that country. Also got DPI, which is per capita disposable income in dollars, and DDPI, which is the percent growth rate of the per capita disposable income in dollars. Now that we have that, let's take a look again back at our code, and I'm going to load the data. Okay, so I'll run that line there, and I'm going to go ahead and build a linear model. I'll call it LMOD. Build a linear model for predicting the savings rate based on the percentage of population under the age of 15 and the percentage of the population over the age of 75 and the per capita disposable income in dollars and the percent growth rate of DPI. Okay, and then this, of course, this is telling R to use the savings data. Just to remind you, or if you didn't know, the 1M summary, this is a command from the Fairway package. Just gets you a smaller, more streamlined summary. I'll go ahead and run those two lines of code. So for example, the coefficient for the per capita disposable income is kind of small, at least with respect to the other numbers here. Again, what is small? There is no small, there is no large. It's just, one thing can be smaller or larger than another, but in magnitude, it is smaller than all the others. But note what exactly this is telling us. This says that the savings rate is decreasing at a rate of about 0.033690% for every $1 increase in per capita disposable income. So maybe we could change the units on per capita disposable income from dollars to thousands of dollars. This will change our coefficient. So we can do that here in these next two lines of code here. I'll build a new model. I'll call it LMOD2. Okay, I'm going to build this model, SR based on all the same predictive variables as we did before, but in this case, I'm going to take DPI and divide it by 1,000. Okay, so when I run those two lines of code, here's my output. Now you can see then that that coefficient has changed. It's still the smallest in magnitude out of all the beta estimates, but it's certainly on par with the others. It's not that different. It still says exactly the same thing as it used to. Okay, but maybe now it's more easy to interpret. When I look at this previous output right here, gosh, I see all those zeros and that gets confusing and stuff. I can look at this and interpret that much more easily, I think. It says that the savings rate still decreases because of the negative sign there, decreases at a rate of about 33.69% for every $1,000 increase in per capita disposable income. Okay, that's just, that just seems a little bit more natural to me. It's easier for me to think about, 34% than it is to think about 0.03369%. Okay, notice that all the your t values and your p values, they remain the same. Okay, they haven't changed at all. The only thing that's changed here is, of course, your coefficient and also your standard error. And that makes sense because really, your standard error has the same units as your estimate, right? So if you change the units on your estimate, then you're going to change the units on your standard error, and it's off by, guess what, a factor of 1,000. You can actually automatically standardize variables. You can use the scale command, and when you do this, I believe the default is it'll actually standardize by the mean and the standard deviation. So it subtracts the mean and divides by the standard deviation. And remember this, now once I do that and I want to build a linear model for SR. Okay, so in fact, let's just run this first line of code here and then compare our original data set savings with the scaled one. Okay, so let's run that, and I'll just come down here into the console and let's just take a look at the head of savings, and then also take a look at the head of scaled. Okay, so you can see that scale command has been applied to all 1, 2, 3, 4, 5 variables. The predictors, all 4 predictors, and the response. We have rescaled the response and all 4 predictors. So now if I go back up here to my code, and if I take a look at building a linear model for SR versus all the rest, right? That's what that is short for, so that I don't have to type in all of the predictor variable names. Then this SR is really different from the original SR. It's rescaled, okay, because I'm using the scaled data set. If I build that model and take a look at the summary there, then yeah, here's my output. This time the intercept is, well, it's supposed to be exactly 0. It appears to be a little off, but that's just due to some machine error, some computational error. Because remember, the regression surface always passes right through the origin after you standardize your response variable and all your predictor variables. So the y-intercept there, the vertical intercept, ought to be exactly 0. The t and p values are all the same as they were before. Okay, you can compare these all these t and p values to the ones that you saw up here. Okay, they're the same. Just spot check here: 3, 3, negative 1, 0, 2, 3, 3, negative 1, 0, 2. Oh, wait a second. Look, the first ones, these are different. Only the t and p values for the intercepts are for the intercept. The t and p value for the intercept will change. Okay, but for all your partial slopes, they remain the same. And take a look at this. Now the t-value is actually right at 0 for the intercept, and the p-value is exactly 1. So you might think about why that is. Now the residual standard deviation has increased from, what was it before here? 3.80267, right? That's the residual standard error, to 0.84873, whatever that is, okay? And that's just because if I take 3.80267 and divide by the standard deviation of savings rate from the original data set, 0.8487332. It should be more or less exactly that number. What about the coefficient on POP 15? It was negative 0.46119. But what have we done now? We've rescaled the predictor variables and the response. So what should the new one be? Let's see, I'm going to have to multiply by the standard deviation of POP 15 and then divide by the standard deviation of my original SR, okay, to get negative 0.942, which is exactly that, negative point, right, 0.942, because this is 10 to the times 10 to the negative 1. Okay, so that's how those get adjusted. Now, when the response and all the predictors are standardized this way, that is, in sort of the standard way by subtracting the mean and dividing by the sample standard deviation, then all these model coefficients will be between -1 and +1, right? If you look at all these, your intercept, then it goes straight to 0, and all of these model coefficients are numbers between -1 and 1. Or between 0 and 1 in magnitude at least, and then with some sign attached. And these can be viewed as correlation coefficients, or sometimes we call them partial correlation coefficients. In fact, remember that if you just had one predictor variable, we studied this back in the first couple units of the course, but if you just have one predictor variable and one response, and you standardize the response and that one predictor variable and make a simple linear regression model after standardizing, then the slope coefficient for that standardized model is exactly R, the linear correlation coefficient. When you have multiple predictors, you can view these as sort of the same way. Okay, these are sort of, we call them partial correlation coefficients. They sort of represent the effect that a one standard deviation increase in a predictor variable has on the standardized response. Okay, so in a sense then, kind of sort of, in at least in some way, the more you can, so in a sense then, maybe which one in that sense is most significant. It looks like the POP 15, the idea is, if you increase this POP 15 variable by one standard deviation, it decreases the standardized response by 0.942 standard deviations. Now, when the predictors are on similar scales, it can be useful to make simultaneous confidence intervals for the coefficients. Sometimes people make a bunch of confidence intervals simultaneously for multiple things, but sometimes, it may or may not be more useful to make simultaneous confidence intervals, meaning that, you set a family level of confidence and maybe use the Bonferroni adjustment. So that's what I'm going to do. This next chunk of code will get me simultaneous confidence intervals for the betas. Let's run all this and see what happens. I'm using the ggplot2 package there. Here they are. That is, we can be 95% confident that this interval contains the true coefficient for pop 75, and at the same time that this interval contains the true coefficient for pop 15, and that this confidence interval contains the true coefficient for DPI, and that this interval contains the true coefficient for DDPI. Notice that there's a vertical line right here through 0, so it's sort of saying also that there's insignificant evidence to conclude that any of these are different from 0. Of course, there's also insignificant evidence to conclude that this one is different from, say, a quarter, and there's insignificant evidence to conclude that that the coefficient on pop 75 differs from -1. Okay, so you got to be careful about that, but certainly it looks like no matter how you look at it, the coefficient for pop 15 seems to be statistically significantly different from 0, so maybe you at least want to include that guy in your model.